We're talking today about chemically reacting turbulent flows, okay? We're going to be talking about those in the context of batch systems, continuous systems. We're going to talk a bit about slow chemical reactions, fast chemical reactions, competing chemical reactions, how we build these things, how we set these things up, and how we interrogate some of the physical output. So I wanted to start, unfortunately, today with just some working examples, which are hard to do when I can't log into my computer. One was to demonstrate a batch system where we have a bolus addition of an acid to a tank filled with a base and watch the time evolution of that reaction produce some salt. And see the competition between mixing, reaction, and the consumption of the rate limiting reactant. We'll then do a continuous flow system where we have two streams coming together over a static mixing element. And again, watching how we reach some sort of steady state production at the outlet as a function again of mixing and the degree of the ratio of the two reactants. We'll then go back into the slide deck where we talk about more complex cellular reactions. I spoke about this in weeks past, or in seminars past, I should say, when we talked about large large molecule growth and looking at how we can feed these different cells with oxygen and glucose and whatnot to achieve a target titer production and cell density and maximize cell density, I should say. And again, be able to incorporate those in simulations. And then last talk about equilibrium systems, where we have, say, a buffer bicarbonate system, where we have carbon dioxide informing pH and modeling the two or all the constitutive reactions as well. So again, my machine's still booting up, but Eric, if you don't mind being my hands, I'll go ahead and talk through some of these examples and share on your screen. I'll work through what I meant by these kind of competing reactions. And so, Eric, if you don't mind, share and open up a blank M-Star, and I'll show what's going to do. It looks like you got something here almost ready to go. And okay, so I'm going to squint here and see. So here we have a simple agitated vessel, a simple Russian impeller spinning some tank, and we have one scalar field defined. You'll notice that the scalar field has a child geometry shown here as just some sphere. And Eric, if you don't mind, just move that to the top of the tank, representing some sort of bolus addition. So what we have here is very familiar. An agitated vessel with some bolus of scalar field being added to that region defined by that cell, that sphere. So we're talking M-Star here. We're using M-Star here, but the physics we'll be describing will be more general. We're using M-Star as the engine to simulate and understand these physics. Eric, if you don't mind the scalar field, let's rename that acid and just define it as the acid bolus coming into the vessel. And let's define some sort of initial child geometry as like 1 mole per liter, if you don't mind. I think you've got the setting set to moles. So make that 1 mole per liter and make an initial injection. So physically what we're doing here, guys, is we're defining a scalar field, which has advection and diffusion and the possibility for reaction. And we're defining the concentration at T0 to be 1 mole per liter inside this sphere. Now, the action of the impeller is going to cause this acid to evolve throughout the vessel and eventually homogenize. And so if we do nothing else, this would be nothing more than just like a blend time characterization where we'd see the scalar field evolve throughout the vessel and eventually become homogenized following this addition. Eric, please go ahead and add a second scalar field and let's name it base. And again, we're using M-Star as the vehicle to talk about these reaction kinetics. When this starts to cook, the platform is less important than the physics we're seeing. Perfect. Okay, and let's go ahead. And there's no child geometry here. If you don't mind, delete that child geometry, because here we're not going to say we have a bolus addition of base. We could. We're instead going to define a background concentration. And Eric, if you don't mind, change that background concentration to like 0.01 moles per liter. So what we're defining here, guys, is an already mixed, an already uniform distribution of base across the system. So again, we have a bolus of acid being dropped in to this uniform distribution of base with a molarity of 0.01 across this fluid domain. We could do a second bolus addition. We could let that fall in and mix and watch the reactions go on. But heretofore right now, we just have two species. One's initially uniform, that's the base. The base, and one is being added in this bolus, that's the acid. And so both of these are going to advect and move throughout the fluid. It just so happens that the base isn't going to do much because it's already homogenized. Now, lastly, Eric, let's go ahead and add a reaction. Let's add one more scalar field as the product of this reaction. Please add a new scalar field. Let's name it salt. This is just a holding pattern. Rename this guy salt. And now we're going to say that there is no initial salt concentration inside the vessel, no background. There will be no bolus addition. So right now, this salt scalar field exists, it's being pushed around, but nothing is happening to it, right? It doesn't exist. Its concentration is zero throughout. The way we're going to get salt is through a reaction. So Eric, if you could please add a scalar field reaction, let's go ahead and specify this. Perfect. Let's go ahead and edit this. So when we're defining this reaction, we can define the reaction rates of all three species. You'll notice them defined on the right. We have a rate acid, a rate base, and a rate salt. Now, in principle, these can be arbitrarily complex expressions, okay? In practice here, we're going to define these as a simple first-order rate kinetics. So Eric, if you don't mind, define a variable just named float reaction rate and define it to be 0.1 or whatnot, okay? Perfect. What we're writing here is just some sort of empirical rate constant. So this has units of moles per liter per second, okay? And if you don't mind annotating the end of that reaction rate with that unit, Eric, just so we can keep our heads about our tails. I'm sorry, it should be inverted of that. It should be seconds per molarity squared. But either way, you can get where I'm coming with this as I attempt to make the units homogeneous throughout. Foundationally, this is going to define how fast this reaction is occurring. Now, this reaction rate is not something we're calculating with the code. Yes, we could indirectly calculate a reaction rate if we ran multiple simulations and compare results to empirical data, but oftentimes these reaction kinetics are things we know. Now, to speak to that a little later about how we extract these things, we're going to say that this value is known. Now, Eric, if you don't mind, let's define that you're doing it already. Yes, the consumption of acid and base due to local concentration of acid and base. And so Eric's typing here is we have a rate acid is equal to minus the reaction rate times the local concentration of acid times the local concentration of base. So what's going on here? Yeah, go ahead and plop that in. Perfect. And we'll do it times base. Now, this should look familiar. This is just a simple rate equation describing how acid is being consumed in response to the local concentration. Now, importantly, this reaction is occurring on a voxel by voxel basis, which means that inside each voxel, we are looking at the local concentrations of acid, looking at the local concentration of base, calculating a local reaction rate, and using that to inform a local time evolution of the concentration, okay? So these are not global values. We are doing this in each individual voxel. If you don't mind, Eric, let's repeat this syntax for the base, because those are the same pairwise reactions. Perfect. You can copy paste or rewrite per your liking, and then we'll go ahead and define the same. Yeah, you got it. Perfect. And we'll define the same now for the salt, only the opposite of the rate. You got it. Perfect. Now, why is it the opposite? Because salt is being produced. Salt is being produced by this at the same rate at which the acid and base are being consumed. So if we look at this carefully here we have these reaction kinetics specified for each species. And what's happening is that on top of the advection diffusion, which is occurring behind the scenes as these fluids get pushed around by the impeller, there will be the superimposed reaction occurring in each voxel. Okay, Eric, close out of this if you don't mind it, okay? And let's go ahead and make a resolution maybe 150 or so we get a bit more granularity. And let's go ahead and run in the resolution, of course, defining the fineness with which we're resolving this flow field or how much of the turbulent spectra we're resolving explicitly. And let's boot this up. Beautiful background, by the way. That picture right there, that's stunning. That's a lovely background. It's a good one to have, considering you're kind of doing a surprise screen share. Okay, let's go ahead and run this now, and let's get ready to post-process and watch how this guy evolves through space and time. So we can just see your background, Eric. We don't see your screen anymore or any of the M-Star stuff, just FYI. But there it is. Yep. Okay. And if you don't mind, hit run, and we'll begin post-processing and watching this guy go. For those interested at home, Eric's running in Linux, which is great. Right? Is this nice DCV you're logged in through, or is this just Linux machine?
Yep.
Very good. Okay, boot it up. So here this thing goes. And if we look at this output here, we see acid, base, and salt, as it were. Now, if we look very carefully, and we're going to post-process momentarily, We're about 2 seconds into the simulation, and look at those concentrations. The acid concentration, if you squint, it's going down. The base concentration, if you squint, is going down. The salt concentration, if you squint, is going up. Okay. Look carefully at the acid concentration RSD, which describes the degree of homogenization. It's going down, implying that this acid is it's still very, very high. It's still locally concentrated, but we're getting some we're diffusing, we are diluting, we are getting this acid better, increasingly distributed across the system. Likewise, salt is becoming more distributed as it evolves. Base is showing a little more heterogeneity. We're about 97% homogenized, but foundationally, that's fluctuating around as we're consuming local base. Eric, if you could please open this up in post, let's visualize what's going on, and we're going to look at the 3D volumes, if you don't mind. And for those really keeping score at home, my Windows update is at 91%. And I don't know what time it is, but it's 35 minutes approximately. Okay, let's maximize this to fit in our screen. It looks like you're bleeding off screen a little bit, at least from my end. And perfect. Okay, so here we see a snapshot of the velocity field after 11 seconds, which is great. We can see the Russian impeller pushing fluid around. We can see, if you squint, some of those kind of double loops, as we have the top region being pumped down to the bottom region, all characteristic flow. If you don't mind, Eric, let's choose to color our three-dimensional field by acid, which is what we added to the top of the vessel. Okay, are we showing acid here? I can't quite see it. Is this the acid?
This is the acid, yep.
Okay, so if you don't mind, let's play this and watch the evolution of this acid as it moves through. There was our bolus addition. Here we see it being homogenized under the action of the impeller. But wait, there's more. In addition to being agitated under the action of the impeller, this acid is being consumed by this ongoing reaction kinetic. If you don't mind, and refresh at your convenience. Yeah, thank you, Eric. And we can see here, and you can even, if you want to, render the tabular data and show the plot showing the RSD as well as the mean. Perfect. So here we can see our RSD going down from this fundamentally non-homogenized state down to something that's becoming somewhat reasonably mixed, at least 50% homogenized, better than it was before. So we can see the right-hand plot, this time evolution of the concentration of the RSD converging towards that of a well-served system. The left plot is showing the amount of stuff we have. And we can see that the amount of stuff we have is decreasing. We started off with a mean concentration of about 6 millimole. And after about 20 seconds of operation, we've dropped to about 0.1 millimole. Why? That's the reaction. The rate at which this is decreasing is strongly correlated to both our reaction kinetics and the rate at which this is mixing, okay? And if you don't mind now, Eric, let's go back to our, so foundation, if there was no reaction, that black line would be constant. It would be constant because advection and fusion don't change mass. They just push it around. Is the presence of the reaction that's causing the total scalar quantity to go down in time. Eric, render by salt, as I think you're doing now. And let's go ahead and back to our initial view. Let's go ahead and watch this salt evolve here. Okay, so here we have some salt. It's a very small quantity of salt initially inside the vessel. We might need to be mindful of our color scale there. Yeah. And let's go ahead and play and watch the salt evolve throughout this vessel. That's, yeah, perfect. Yeah, recalibrate to that and go back to time 0 and play again. Perfect. Okay, so here we can see the time evolution of this salt as it's being produced. Now, again, if you don't mind, go to that scalar field one more time. I'm sorry, the tabular data for salt, Eric. Let's watch this. Okay, here again, we see the salt production, the salt concentration, mean concentration going up because we have this reaction ongoing. Beyond just this aggregate data in the plot here, we can actually see where the salt is across the fluid. We can see where it's being produced, and there's competition between production and homogenization. And I can tell you right now, guys, this homogenization time is on the order of like 30 seconds, 40 seconds, which isn't surprising because we have an impeller spinning at 60 RPM. The reaction rate, this thing is only gaining, a few millimoles every 60 seconds or so. So this is clearly a reaction-limited process. We have no problem homogenizing this vessel. That is just because we have a reaction in play, that's fine. But you can see already that we're not limited by mixing, we're limited by reaction rate. This thing is mixing very quickly relative to the rate at which reaction is occurring. And so we go back to our 3D view, Eric, what we'd see, rather what we would not see, are strong variations in concentration. We would instead see essentially uniform tank color changing as this thing reacted slowly relative to the blend time. Okay, let's go ahead now, Eric, and let's make one adjustment to this model. If you go back to pre. Perfect. Now, how can we make a system that works at the other end of this extrema? We want a system where the reactions are fast relative to the mixing. Option 1, drop the impeller speed. Option 2, which we'll exercise today, is we'll increase the reaction rate. So if you don't mind, Eric, go over to the reaction rate. Yeah, then let's bump that up by 2 orders of magnitude. Let's go ahead and make it 10, okay? And let's go ahead and rerun the simulation. And you can stop the other one since it served its purpose. And we're going to rerun this and watch and compare the results. So go ahead at your convenience and boot this guy up. So it's all the same logic. We have local reactions. We have this competition between local concentration, local reaction rate. But here we have reactions that are occurring much, much faster. So if you don't mind, Eric, let's take a look here at this screen here that's processing. Some same general rules of the road. We're losing acid. We're losing base. We're gaining salt, as it were. But importantly, this reaction rate is now occurring 100 times faster than what we were seeing previously, okay? Whereas it would take 10, it would have taken, minutes to realize the full reaction with our previous state. We can do the same reaction will happen here in seconds, which is on a time scale comparable to blending. So Eric, if you don't mind, can you please go ahead and visualize this in post, and we'll again be using the 3D views. Perfect. Okay, let's go over here to our salt and to our base.
Do you want to look at the tabular data or the?
Sure. Either one's great. Yeah, we can attack it with either data, either set first. Awesome. Okay, so this is really interesting, and we're going to visualize this as well. But look at the time evolution of the data here. There were the slope of this curve describes the aggregate reaction rate. Initially, it was very fast. Then it was very slow, and then it picked up again. What we're seeing here, guys, is this competition between mixing and reaction kinetics. Initially, there was plenty of reactants to participate in the production of salt. As time went on, we consumed all of the base that was available for the acid to gobble up. As a consequence, because we hadn't homogenized, we're nowhere near homogenization, we stalled. The production of salt was stalled because the reaction was occurring faster than mixing. Okay, that's what that plateau means. And we're now seeing this competition between mixing and reaction kinetics. And we're seeing the adverse effects that slow mixing time has relative to reaction kinetics that's leading towards this these kind of non-uniform and non-constant reaction kinetics. So Eric, if you don't mind here, let's color this by, where are you at here? Are you showing the salt? Or the base?
This is the base.
The base might be less interesting unless you happen to have that injection bolus immediately on a plane. That might allow us to see the base getting gobbled up. Do you know if it was on the plane?
This is in the volume. So
yeah, when you did your base injection, was that on the plane or was it just like in a random spot in the vessel?
Well, the base was the background.
Okay, yeah. I'm sorry. The acid, was that on a plane or was it?
I don't know, but okay, but yeah. Anyway, I'll switch over to the salt.
Let's just see what we got. Okay, so here's our salt. Let's go ahead and watch this go. So what we're going to see here is this immediately. Go ahead. Perfect. Okay, we'll watch the salt form up. Okay, it formed and it's being dispersed and it's being produced quickly, much more quickly than it can be homogenized. So if you don't mind, Eric, let's go back to that tabular data showing the time evolution of salt concentration. Okay, and here again, we can see some of this rate limiting process where we have the plateau at time 0. We can see the getting homogenized, leads into a much faster rate, but the rate is plateauing. Eric, if you don't mind, please go over now and let's take a look at the tabular data showing the acid concentration. Understand what's going on here. Okay, and we can see here that our acid concentration across the vessel is getting low. In fact, we're gobbling up all of our acid. We're gobbling up all our acid in about the time it takes the acid to blend for the system to homogenize. In fact, what we're seeing here now is about equal parts competition between reaction and blending. And so again, what we can see with this is not just the overall effect of this behavior, but the local physics and local competition between these things in terms of the 3D view and the 2D view. And in fact, Eric, if you don't mind, go to one last of these 3D views. Let's please render the base. And let's see if we can see the base concentration going down a bit as the acid starts to gobble it up. Is this base?
This is the base. Yep.
Okay, let's go ahead to time 0 and watch what's happening here.
So you can see it start to decrease in there.
We're
and
gobbling up base in those regions, okay, where we would expect, or we're seeing this competition again between the mixing and the homogenization. So again, just coming up for air here, as it were. What we can do here is see this competition between local mixing, local reactions. We can see both the aggregate effect, as it were, as well as the local effects, understand how we might modify the system to achieve a more targeted or tailored output. Okay, let's go ahead now. And I wanted to get onto an open system, which is going to be pretty analogous to this, but I'm not sure if I'm going to have time for it. How are we doing on time? I think we can. But happily, I think I can join the call. Let me just see if I can't get joined here. Eric, you don't have to be the hands anymore. Although I may need you to be the hands because I still have a couple hiccups here waiting for Teams to join. Okay. So Eric, if you don't mind, if you could please, actually, I got it. I'm going to share my screen. I'm back in action. And let me join here. I'm going to come on in. Folks, can you hear me? Am I functional and live?
Yep, I can hear you. I can see you.
We're back. Thank you so much, Eric, for being my hands. Let's jump back into it here. So let's now jump in. Let's continue this kind of discussion with the idea of an open system. So we have the same logic as was being applied earlier. We have these species reacting, but instead of being some sort of bolus addition, we're going to define this as being some sort of continuous flow process. So if I have CAD, I'd use CAD. I don't have CAD handy right now, so I'm just going to make some sort of T-junction, as it were, and define this kind of impinging jet mixing process that shows how these two species interact and move throughout the system. Let me go ahead and make this guy a little bit longer here so I can get some of this reaction downstream.
You're not sharing yet.
You go ahead and push this. Thanks for that cue. Share screen. And can you see me now?
Yep.
Good. Perfect. Okay. Let me go ahead and do the same kind of thing Eric was defining here, but I'll make a continuous flow. We are again going to see this competition between mixing. We are still going to see this competition between reaction, as it were. We're going to see it within the context of a quasi-steady state system. So let me go ahead and add my first scalar field here. Same logic Eric had, but instead of a child geometry, I'm going to have the acid just come in through a boundary condition. So its initial injection region here is not going to be along a bolus. It'll be along the boundary condition. So I go over here to static inlet or outlet and go ahead and choose my edges. I'll go ahead and click on this guy here and define this as my main inlet. Let me go ahead and again say that the acid is coming in the main inlet with a specified value of 1 mole per liter. I'm going to create another static inlet or outlet. I'll define this on the edges here. I will flip this and call this my second inlet. And now I'll define this as the location of my base. Skip the child, I'll rename this base, and I'll say that the main inlet has 0 base, and the secondary is all base. Okay, we'll say it's coming in with the concentration of 1 mole per liter. Just as the main inlet, if I look at my acid here, there's no acid coming in here. We can do mixtures, we can do time variant stuff, of course. We'll just have these 2 constant species coming in. I need one more boundary condition here. We'll call this my edges over here, my drain. I will flip this and just call this my main outlet. And I'll define this as just being some sort of pressure boundary condition, okay? I got pressure boundary condition. And just to keep things interesting, I'll make this a bit more viscous, just so you can kind of see some interesting effects here. And just to keep this interesting, I'm gonna go ahead and add a little bit of a some more topology here. I'll add a little bit of some miscellaneous twist element static mixer excitement. So I'll resize this guy to be the appropriate size. Let me just kind of get him here. I think that was my vessel diameter, my pipe diameter, and I'll move this downstream just to give us a little assist. Again, I'm using built-in stuff in M-Star. If you've got CAD, by all means, use the CAD. Don't just limit yourself to this. So what is my concentration of the acid at the main outlet? I don't want to specify a value. I want 0 gradient. Come what may. I don't want to overwrite what's coming at that outlet. Likewise, for the base, I don't want to specify what the concentration should be at this moving outlet. I want it to be 0 gradient, come what may. And just as Eric did, I'm going to create one more scalar field. I'll skip this and call this a salt. Same logic applies. Salt's not coming in the inlet. Salt is coming in the second. It's not coming in the secondary outlet. And for the outlet, neither the inlets have any salt. For the outlet, 0 gradient, come what may. So how was salt going to get inside the system? Salt was going to get inside the system because of the reaction. Now do a very similar reaction to what Eric specified previously. So I'll give these just so I can show some excitement here, I'll give these guys a bit of a ramp, as it were, so you can watch the velocity go on up. And I'll go ahead and define a reaction here, just as Eric did. I'll define my same reaction kinetics, rate base, rate salt. And I'll just define this as being minus rate acid, just going to make it efficiently, saving crucial keystrokes here by just reusing what I'm going to define up here. And I'll go ahead and define here this float reaction rate. And again, this is C++. You write anything you want to write. You get a very complex, I'll show this momentarily, much more complex reaction. But at the end of the day, I'll define here my reaction rate times my salt times my acid times my base. Okay. So at the end of the day, here I've got more reaction kinetics. And just to be clear, you can obviously double check all your codes and whatnot as you're building them. But this one's checking out just fine. Okay, and it's just, so I can see or have these notional values of a concentration of 1, an acid concentration of 1 or acid concentration of 0.2 and a base concentration of 0.2. Lo and behold, this isn't all surprising. What my reaction rates are going to be as it goes through and checks this code, 0.2 times 0.2 times 1. So it's nice to be able to kind of check the code on the fly before you run it. Okay, let's go ahead and run this now. So we're going to have this salt being produced by this ongoing reaction. And rather than just being unilaterally consumed, as we saw inside the basic system, inside the bolus system, this guy will be gobbled up, as it were, by these, operating at a steady state. So let's run this. Let's go ahead and get this guy going. A better reference diameter would be Y here, since that describes my diameter. And I'll make that resolution like 50 or so. So we have 50 or so, maybe 80 or so points across that diameter to make it clear what's going on. Okay, let's check. Model check succeeded. Let's save, because I don't want to have my computer restart again and lose everything. I'll call this just continuous reaction. And let's run. Okay, oh my gosh, this is just hilarious. This is laughable. It completely has okay. Maybe we're good now. I can't believe how hard it refreshed my computer. Let's go ahead and run this here. Okay, off we go. One key point here, and I just saw this for those who may use M, so that's how I did it. I did my flood fill point in the right location. Let me just edit this guy real fast and move this flood fill point and just get it inside my domain. Okay, that way it tells the code that this is where I want action to happen. and that is where I don't need action to happen. One more time, and hopefully this kicks off without an issue. Okay, off it goes. So here we have these species fields moving through. We have our velocity fields booting up. Let me see where we're at. I'll do a quick right here to look in. So I can see here that I'm moving through time, and after 1 second, I should have my steady state flow conditions. But if I go into post right now, I can begin to see the time evolution of these velocity fields and how these species begin to come together. So I'll let this guy boot up. Here I am watching this flow start to evolve. Okay, I'll continue to get more data here. Quick write is your friend when you're kind of wanting to see data on the fly. It kind of forces a print. So I'm watching these guys boot up. I'm beginning to see the flow field evolve throughout the system. I can see some of this flow field evolving down here. I'm only a fraction of a second in. Let's go ahead and color this by our scalar fields. So if I look at my acid, let me go put it on my Y plane here. My acid is coming in through my acid inlet. My base is coming in through my base inlet. And my salt, well, guys, there's no salt, which isn't surprising because we have these not having to touch each other to produce any sort of reaction. And if I look at this here, I can see, for example, my acid is the way to go. Let's go ahead and kind of get this show on the road a little bit. Knowing that I kind of want to see these things mixing faster, I'm going to go ahead and walk back on this ramp and just kind of let these guys boot up more quickly. And I'll also drop my resolution just to get this show on the road some. Let me go ahead and bring this down like a 40, which would be sufficient for me to see what I need to see. Okay, off we go. So one of the things I do like about running M-Star on GPUs is you're not, immediately what is going on in the simulation. You're not waiting, hours to see like whether it's gonna, how these conditions are coming together. It's you can update immediately on the fly, and I think it's a very satisfying way to use the code. Okay, so here we're going to begin to see these guys coming together a bit more quickly. I can see acid and base coming in a bit. My main outlet is getting some sign of life, and here I can see, as did before, some salt being produced. Let's go ahead and watch this here. So I've got my flow field. Here I am. I'm beginning to get at a steady state flow, a velocity field. Let's go ahead and snap over to the Y plane and let's look at acid. So here's my acid coming in. It came in with uniform concentration. It's leaving with a lower concentration. In fact, if I look at my mean concentration of the outlet here, I can see my acid concentration is lower. Let's say look at my base. Same logic applies. I've got lots coming in, but it's below 50% leaving. Why? Because I'm getting salt. Salt's being produced. And we can see here how this mixture of the acid and base is informing this non-uniform production of salt across this cross-section. 3D views are our friends for reacting systems. So I'll do I'm getting one right now. Let's go ahead and reload all this data and go to our 3D volume. And here we can see kind of the spatial distribution of this salt as it goes through the static mixing element. So there we see our velocity field. Let's go over to our volume resampled, go over to our salt, as it were. We can see where salt is being produced. We're getting salt right there, which isn't surprising. We're getting salt up here where the two jets come together. We're getting salt in this vortex region behind the impeller. But foundationally, we're seeing directly the effects of poor mixing on poor salt production. We're seeing the effects of poor mixing, I should say, and poor flow ratios on underutilization of our two species. Look at this, guys. My salt is going to plateau here, this mean salt concentration. It's plateauing at steady state conditions at just a few moles per liter inside my millimoles per liter inside my vessel. I am getting a very, very poor utilization of these two reactants in terms of the amount of product that's being produced. And that's fine. I just ginned up the system. Some obvious changes would be to make this longer, add more mixing, change the flow rates, increase the reaction kinetic if I could. But point blank, being able to diagnose kind of where these reactions are occurring, how useful these reactions are, how efficient they might be, it's a really, really nice way to kind of understand turbulent reactive systems. Okay, so I've spoken about the simple batch and the simple continuous flow systems. I've discussed this previously, so I'm going to lean this to some of what I discussed on previous webinars, but I do want to emphasize that these toy reactions these little acid-base neutralizations, they're great, but they're just toy reactions. We can do far more complex things when we have this C library available to us to run these codes. And as discussed before, we can do multiple competing species with more complex reaction kinetics. Here, for example, I've talked about this before, is the production of biomass, then the consumption of glucose, glutamine, lactate, the production of lactate, the production of ammonia, production of titer. These are kind of standard, and these can be tweaked in various forms, ways of describing how these competing species interact. That's good to do in M-Star. That's no problem. In fact, this is what it looks like in practice. If I go to something like this and open what I was showing earlier, here are those reaction kinetics. I have more scalar fields, of course. So this is like more than just acid, base, and salt. I've got DO, glucose, glutamine, lactate, ammonia, BCD, viable cell density. I can put titer in as well. Doesn't feedback anything. But foundationally, guys, if you can do it for 2 species with a simple reaction, you can do it for N species with a very complex reaction, where I've got these kind of full reaction kinetics specified inside the reaction UDF with intermediate variables as well, such as maintenance coefficients, cell death rates, cell growth rates, as it were. They're being calculated on the fly as a function of the local concentration. So I know I went from like 101 to 501 in terms of a college education, but foundationally, like, this isn't a lesson, it's more of an announcement that if you can do 2 with simple, you can do N with complex. And realistically, the ability to be able to solve those things, on the fly, as it were, in tandem with the reaction with the turbulent kinetics, I think is pretty compelling. And so don't let the simplest of those first 2 examples fool you. It is very easy to generalize this to be a very complex, chemically reacting system where we have oxygen being gobbled up, glucose being consumed, cell density changing, all within the context of one kind of chemically reactive turbulent system with these competing systems. And what I like seeing here is the oxygen dead zone. For anyone that does work with bioreactors, this should make your chest tighten when you see these disparities in DO, which are well known to exist. We've published on them, we've talked about them, they've been measured. And being able to see them in tandem with the other reaction kinetics and BCD is very compelling. You can put these all in one framework. Okay, let's jump ahead in the interest of time because I was late. Start talking about kind of faster and more complex chemical reactions involving competing species. A great example of this comes up repeatedly are these buffer bicarbonate reactions. Now, what's great about these, they're pretty well characterized. What makes them a pain from a simulation standpoint are the disparity in reaction rates. So here we have a familiar process. We have carbon dioxide that reacts with water to produce this carbonic acid, right? But we also have the production of carbon dioxide via the decomposition of carbonic acid. So CO2 has both sink and source terms, as well as any sort of action of the biomass during respiration. Carbonic acid has the same dance. It's produced by the reaction of CO2 and water. It gets gobbled up as it decomposes into CO2, as well as these bicarbonate ions and hydrogen ions. The bicarbonate, same story applies. It gets produced by the decomposition of the carbonic acid, but it gets consumed as it reprotonates to perform carbonic acid, and the protons have a very similar song and dance. So we can recast. This is differential equations 101, being able to recast this sort of equilibrium reaction kinetic into a series of rate equations, but these are what we need. This is what the code needs in order to evaluate the time evolution of these individual species. And just as I did before, we can model these local rate kinetics, use the local concentrations to predict local pH, for example, as a function of local CO2 concentration as it cascades through the equilibrium process. Now, the problem with this and the challenge is that some of these reactions are far faster than others, okay? The reaction of CO2 and water and the decomposition of carbonic acid into CO2 is comparatively slow compared to the deprotonation process, okay? Said again, these are on the order of 10 to the 7, 10 to the 10 reciprocal mole seconds. I would argue that this is not a number anymore. It is a concept. It is the idea that this reaction is instantaneous. And in fact, these reaction rates are hard to measure. We can measure their ratios, the equilibrium quantities, very easily, but the rates are tough. These rates can be measured. You can just watch the reaction occur. These rates are very difficult to measure. And so as a consequence, is it really 10 to the 7 and 5 times 10 to the 10? Well, we know the ratio is 5,000, but I think the constant here is these are instant. And now when you have instant in a simulation, that makes it hard, okay? You can do it, but it requires a bit more of a sophisticated integration scheme. If I go into this guy here, it's the same logic that I discussed earlier. Here we go. We've got carbon dioxide, carbonic acid, hydrogen, and carbonate ions. We can calculate local pH, of course, from the concentration of hydrogen. Nothing new here. But if I go to my reaction kinetics, here I've got these things with these absurd reaction rates. And like, this can't be modeled using standard, just like Runge cut approaches. You've got to use implicit solution approaches. So there's an M-Star, of course, to handle this. But like, so you can do it. You can model these super stiff things. You can handle it okay. But it's kind of like, what's the point? Because if we go a bit deeper and appeal to equilibrium kinetics and recognize that these reactions are instant, we can instead just link things like pH to, or H concentration, to the local CO2 concentration, okay, which is far more familiar. These Henderson-Hasselbalch relationships are far more useful. So to be sure, what does this look like? And again, if you need help driving this, I can help. Like, it's not hard. It's very easy to do. Like, you can do this. You can show how, like, if you start, oopsie, there's my son's French flashcard list. Masculine and feminine words, very interesting to me in French. I don't understand it, but it's interesting. I always get them wrong, but I don't speak French. Okay, so here we have our reaction kinetics. It is very easy to show that at equilibrium, you can recover the Henderson-Hasselbalch relationship. So why not use it? Instead of trying to model this exceptionally fast reaction kinetic, which involves complex integration schemes, because you're trying to bend the corner on a 10 to the 10 reaction rate, well, be smarter and do something like this, where I open this file here, and instead of solving those reaction kinetics, I appeal to Henderson-Hasselbalch, and instead just look at my local pH as calculated directly from this equilibrium constants. This may not always be necessary. This assumes, of course, that reactions are very fast and some of them can be discounted. And it gives us a shortcut for understanding how we can model, how we can save on simulation complexity. For example, there are just two species here, CO2 and O2. The reaction is nothing more than the participation of the biomass in the production of CO2 and the consumption of O2. Then we choose to link local pH to local CO2 via Henderson-Hasselbalch using a pKa and a concentration that are informed by these very complex and fast reaction kinetics. So just keep that, idea up your sleeve. Just because you can do it and you can model it, just because you can describe equilibrium kinetics and fast equilibrium kinetics within the context of a decomposed rate equation, doesn't mean it's the best way to do it. And foundationally, if you can evoke some sort of equilibrium kinetics that allow you to relate, say, pH to local CO2 or whatnot, use it, because it makes simulations easier to run. And again, just to be sure, if people want these files, I'll send them to you. If you want to see, like, oh, how did he build this kind of like model where there's carbon dioxide being added to the system and that's changing pH, it's obvious. I can send it to you to run it, of course. Same thing with the full kinetics. You want to run it, go for it. One point that I'm not going to be able to speak to today, it wasn't even in the cards, was this the idea of fast competing reactions. So you can in M-Star, and this will be a future discussion we'll have to get to in a bit more depth, model Born type kinetics, where you have both a fast and a slow reaction, and the competition between those two is informed by the subgrid mixing. This is a discussion that needs its own entire seminar, and we'll speak to that later. The objective of today's seminar was to talk to more classical resolved reaction kinetics that may be fast or slow, but assume that each voxel could be treated as a gray body. Should we have faster competing reactions, we do need to use Born type modeling. We need to use Baldega type modeling to handle those Born type reactions. That's a discussion for a future seminar because that in itself is quite involved. But foundation, just to come up for air here, guys, just to kind of see where we were. Our goal was to talk about a few different reaction classes. We spoke with the batch system, and that was the foundation. It's easy to add a bolus, watch it blend, and see this competition between reaction and mixing. The same logic applies to continuous flow systems. And if I look at this, guys, running in the background, like everything is just plateaued here. Like I will get like 4 millimoles per liter of salt production inside the system. Pretty poor utilization, and here is where that's being produced. Here's where that concentration is occurring, I should say. Not a super well engineered system, but interesting nonetheless to be able to decompose it. I can do more complicated systems inclusive of cell reactions, because if I can do 2 species with a simple rate kinetic, it is no problem for me. It is no skin off my back to go to far more complex chemical reactions, including the cellular metabolisms, glucose, glutamine, all I was speaking to earlier. Going from 2 to N is not an issue, because if you can do 2 and do that advection diffusion reaction in tandem, then going to N is no problem. The hard part is doing an advection diffusion reaction. The number of species is the easy part. Stacking more on there is no problem at all. So bear that in mind. We're not limited by simplicity. Fast reactions, equilibrium reactions, those are in play too. You can decompose them into their individual reaction rates. That can become a pain if you have particularly fast portions of these reaction kinetics. And so if so, bend a corner, make your life a little easier. Appeal to equilibrium reaction kinetics and use those as well. So at the end of the day, folks, lots of ways to consider these reactions, lots of ways to attack these reaction kinetics. The paradigm is here. The engine is straightforward, and the runtime is phenomenal, I'd say. The key limiting now is you. Like, what can you put in this thing? What can you put in this platform in order to do some really complex things? As evidenced by these models today, there's a lot of options, a lot of off-ramps, a lot of degrees of freedom. Sorry again for the technical hiccup at the beginning. Huge shout out to Eric. Thanks for being my hands, Eric. Thank you so much. I appreciate your flexibility. That's hard to do. Just like sit back and get a cup and watch a presentation, and then suddenly you're the star of the show. Thank you, Eric, for jumping in. Amber, again, thanks for accommodating me as I had my Windows reboot. Glad we pitched in at the end. If folks have questions, I'll take them. If folks want files,
there's a question,
and we'll take it from there. Yes, please fire away.
Okay, just so question first is, can it model combustion with droplets? Yeah, can M-Star model combustion with droplets?
We don't do, no, I'm going to say officially, no, we don't do combustion. Partly because we are not looking at complicated equations of state, nor are we looking at nor do we have any radiative heat transfer, okay? And when you're just saying combustion, I think about physics we don't have. If you are looking at more of an isothermal evaporation process, if you're looking at things like a chemically reactive droplet that dissolves or reacts with other droplets, that's in play. But I'm not going to claim to do combustion right now. But we can do a lot of the ancillary physics just without the complex equations of state or the radiative heat transfer. Good question, whoever asked that.
Another question is, does it have a subgrid mixing model for reactions?
Yes, and we're going to need to, that deserves its own seminar because those models are complex, okay? The answer is yes. You can do subgrid Baldega type reaction modeling in M-Star. It works out of it's here, it's ready to go. But foundationally, the physics associated with those require a lot of ramp up, okay? You can't just show me like, oh, look, here's me doing, this jet and cross flow as Baldega did for 30 years. That'll be a future seminar, and we'll talk about that at length. But that requires more than just a 10-minute segment in this general reaction discussion today. But yes, we can speak with that in detail at a future point.
That wraps it up for the questions.
Guys, thank you for your patience today. I really appreciate you being here. Appreciate you letting me suffer through some updates. Thank you again for Eric for bailing us out with some being our hands. Reach out, emails, questions, files, deeper dives. Reach out. We'll take all the questions that you can give us and take them head on. Thank you so much, guys, again, for your participation.